Welcome back, guys. Today we're going to be starting Unit 7, which is on absolute value and reciprocal functions. So in this unit, we're going to be looking at two specific types of functions. The first will be reciprocal functions, and then we'll get into talking about absolute value functions. We'll also look more specifically at piecewise functions, and then we'll finish off the unit by solving absolute value equations. So for our first topic today, we're going to be looking at reciprocal functions. Now, this is actually a two-part lesson. The first day, we're going to look at reciprocals of linear functions. And then in our second video, and for day 2, we're going to be looking at the reciprocals of quadratic functions. All right, so let's jump right into it. So again, today we're looking at reciprocal functions. And before we get into the specific function, it's important that we do a little bit of background work to make some connections. Okay, so first of all, the reciprocal function is just a special type of rational function. So the unit that we've just finished was on rational expressions and equations. And if you remember, when we have a rational function, basically we have a rational expression or a fractional expression where we would have variables in either the numerator or the denominator or both. And so a reciprocal function, the numerator is always 1. And a reciprocal function has the form y equals 1 over f of x. F of x is a polynomial, and f of x cannot be 0. So if you remember from our non-permissible values in the last unit, we can't divide by 0, so f of x, or the denominator, cannot be equal to 0. So let's just take a look back at reciprocals. So we talk about reciprocals in the last unit when we talk about multiplying by a reciprocal. We also look at reciprocals back in junior high. So if we're reciprocating a fraction, or we're taking the reciprocal of a fraction, we're literally just flipping that fraction. So 2 over 3, the reciprocal of 2 over 3 would become 3 over 2. If we want to take the reciprocal of x, remember that x is x over 1, that would become 1 over x. And if we want to take the reciprocal of f of x, that would become 1 over f of x. So some other things that we want to consider, and this is going to come into play when we get more, or when we look a little bit more at our examples, the reciprocal of 1 is 1 over 1, which is just 1. The reciprocal of negative 1 is negative 1 over 1, which is just negative 1. And the reciprocal of 0 is 1 over 0, meaning it's undefined. Now, if we look at the product of a number and its reciprocal, so if I have some random number and I multiply by 1 over that number, my answer would be 1. So the product of a number and its reciprocal is always equal to 1. If you need an example, I could say the product of 4 and 1 over 4 would be 1. Now, taking the reciprocal of a negative number results in a negative number. Again, I can give you an example there. If we have the reciprocal, if we want to take the reciprocal of negative 3, the reciprocal of that would still be negative. If we want to take the reciprocal of a positive number, the reciprocal would still be positive. Again, we could use a similar example. If I took the reciprocal of a positive 3, the reciprocal would be 1 over 3. Now, one more thing to look at is this sequence here. So we have 1, 10, 100, and 1,000. And we want to look at what's happening as the reciprocals increase. So as the values increase, 1, 10, 100, 1,000, the reciprocals will be 1 over 1, which is 1, 1 over 10, 1 over 100, 1 over 1,000, and so on. So the reciprocals stay positive, but the value decreases. All right, so let's take a look at some reciprocal functions here. So when we're looking at reciprocal functions, we start off with an initial function. In this case, they'll be linear functions. And then we take the reciprocal of that function to get a new graph. So if we take a look at this example here, we have a graph of the line y equals x. And the reciprocal would be to take that function x and reciprocate it. So we would have 1 over x. We're just going to take a look at the values for the original graph and then the reciprocal graph, or the original function and then the reciprocal function. So taking a look at these, if I have x equals -4, so if I look on the graph when x equals -4, that point on the graph is -4. And at -3, my point is at -3, and so on. So I'm just going to fill in this table of values. We would have -4, -3, -2, -1, 0, 1, 2, 3, 4. At point 1/2, we would have 1/2. At point -1/2, we would have -1/2. And at point 1/4, we would have 1/4. Now what we want to do is take a look at what happens to the reciprocal. And so if we look at point -4, well, it's kind of tricky to see on the graph exactly what that point is, but we know that the reciprocal of y is 1 over y, so the reciprocal of -4 would be -1 over 4. And the reciprocal of -3 would be -1 over 3, and so on. So I'll just fill these in quickly. Notice that the positive values stay positive, the negative values stay negative. Now, as we look back at that, you might notice that there were some specific points that either stayed the same or became undefined. So here we have -1. Well, when we take the reciprocal of -1, we also have -1. And we'll get into this a little more with a few examples here, but this is specifically called an invariant point. Notice it didn't change. And then we have 1 over 0 because when we take the reciprocal of 0, we have 1 over 0. Well, that point is undefined, and we'll take a look at what that means in a little bit. And then we have another point here that was at 1 and stayed at 1. This is also called an invariant point. And again, we'll talk a little bit more about invariant points later on in the lesson. If we look at our domain and range for this function, so for the linear function, the domain is element of reals and the range is element of reals. But when we look at the reciprocal function, we have some specific restrictions. If you notice, this graph approaches x equals 0, so approaches the y-axis, but never crosses. So that means that value is undefined at that point. And if you notice, on the horizontal axis here, so on the x-axis, the graph approaches, but it never crosses. So there would be another restriction. So when we write down our domain and range, the domain for the original function is x is the element of reals. The range for the original function is y is the element of reals. But when we get into the reciprocal function, x cannot be 0, although all of the other elements are element of reals, and y cannot be 0, and all the y values are the element of reals. That means that we have a restriction at x equals 0 and y equals 0, but all the remaining values are within the real number system. Now, what I want you to take a look at is the x-intercept of the linear function and the non-permissible values of the reciprocal. So if we take a look back here, our x-intercept for this graph happens at 0, and if you notice, the x values for both of them are happening at the same point, but the y values are changed. So if we take a look at um, so now what we want to do now is take a look at the x-intercept of the linear function and the non-permissible value of the reciprocal. So if we take a look up here, our x-intercept happens at x equals 0 or y equals 0. And if we take a look at our non-permissible value, or where our graph was undefined, that happened when x equals 0 and y equals 0. So we have a non-permissible value right here, and that's where the graph is approaching but not crossing. Now, as well, we want to take a look at the x values for both the graphs and the y values. Well, if we look at our table of values, notice that our x values stay the same for both graphs, but our y values become reciprocated. So in other words, we're taking the reciprocal of the y value. So all of our x values are the same, and all of our y values become 1 over y. All right, so we're going to do just a little bit more background here before we jump into some examples. And there's a new word that I'm going to introduce you to, and that's called asymptote. Now, you may have heard that word before, but we really haven't worked with asymptotes at all until now with 20-1. And so an asymptote, and the P is silent, an asymptote is a line that a curve approaches as it heads towards infinity. So in other words, as the numbers, the x values get bigger and bigger and bigger, the function or the graph will approach a line um, and in some cases never cross it. And the distance between the curve and the asymptote, again, approaches to zero as the number gets bigger. And so there's three types of asymptotes that we talk about. In grade 11 or in Math 20-1, we're only going to look at horizontal and vertical asymptotes, but there is also something called oblique asymptotes, which you'll get into in future courses. Now, with horizontal asymptotes, that would be a horizontal line that the graph is approaching. In 20-1, we're primarily looking at asymptotes that the graph approaches but never crosses. But there are cases where we could have a horizontal asymptote that the graph approach or might cross here, but then come back up and approach but never cross. And so it is possible to cross that horizontal axis. We aren't going to see those a lot in 20-1. Another possible is if we're dealing with a dampening effect, we might have a graph that gets bigger and bigger, or it starts off bigger and bigger, and then eventually it gets smaller and smaller and just keeps approaching that line. Okay, and so those are some examples of horizontal asymptotes that we won't see in 20-1, but do exist. So now we're going to look a little bit more closely at the reciprocal functions. We have on this grid a linear function and then the reciprocated function or the reciprocal function on the same grid. And so I want you to take a look at the two graphs and we're going to make some comparisons here. So first of all, let's take a look at the value of the original function. So where the value of the original function is 0, the value of the reciprocal function is blank. Now, when we're talking about the value of the original function, we're actually talking about y. So if we take a look at the y value of the original function, that occurs right here. Notice that our reciprocal function is undefined. And so where the value of the original function is 0, the value of the original function, or the reciprocal function, sorry, is undefined. And that's where we have a vertical asymptote. And so I could actually take and draw a line right there. And so that's a line that the graph is approaching, but never crossing. Now the x-intercept of the original line is what becomes our vertical asymptote. So the x-intercept of the original line becomes our vertical asymptote, and that happens at x equals 0. If you remember from grade 10, vertical lines are x equals, and horizontal lines would be y equals. Now we want to take a look at what's happening to the values of x when the function is getting bigger, or the values of the functions are getting larger, and the values of f of x are getting larger. So let's take a look at the original function. Where the value of the original function is a very, very small number, the value of the reciprocal function is doing what? So we have the original function getting really, really small. So as these numbers get really, really small, so they're approaching 0, so we're not talking about negatives, we're just talking about when the values of the graph are getting really small. So we're looking in this area right here. So right in there. And so as the values of the graph get really, really, really small, the values of the reciprocal function are approaching x equals 0. And notice this, the closer and closer and closer our original function gets to 0, the bigger and bigger and bigger our y values get for the reciprocal function. So as the original function is becoming a very small number, the value of the reciprocal function is approaching x equals 0. In other words, that reciprocal function f of x is getting bigger. And so when we're talking about this value here, we're talking about positive numbers. So again, we're not talking about whether it's positive or negative. We're just looking at the actual value of the number. Now, where the value of the original function is a very large positive number, the value of the reciprocal function is getting smaller. So if we take a look, as this graph continues to get bigger and bigger and bigger and bigger. So as those y values are getting bigger and bigger and bigger, notice the reciprocal function is getting smaller and smaller and smaller. And so it's approaching y equals 0. In other words, that reciprocal function is getting smaller. All right, so now let's take a look at those values as they get smaller and smaller. So where the original value of your function is becoming a very small negative number, the value of the reciprocal function is becoming a larger negative number. So again, if we take a look at our original function, so we have our original function here, and as they're becoming smaller and smaller and smaller negative numbers, so we're looking right in this area here, notice that our reciprocal function is also becoming larger and larger with regards to the negatives. So it becomes a larger negative number. And then where the value of the original function is a very large negative number, so as this continues to get bigger and bigger and bigger and bigger, notice that our negatives are becoming very, very small. So a very small negative number. And then there's a horizontal asymptote. So where our graph is approaching a horizontal line, that horizontal asymptote is occurring at y equals 0. Now we also want to take a look at where these two graphs cross each other. So I'm just going to erase some things here so we can look at the graph a little bit more closely again. And so if we take a look at where this graph or where these graphs intersect. So we have an intersection point right here, and we have an intersection point right here. And if you notice where the value of the original function is 1, so the value of the original function, so the red function is 1, notice that our reciprocal function is also 1. And where the value of the original function is -1, the value of our reciprocal function is also -1. So if you remember from our chart on the previous page, when we take the reciprocal of 1 or -1, the number stays the same. So where the value of the original function is 1, the value of the reciprocal function is also +1. And where the value of the original function is -1, the value of the reciprocal function is also -1. Now, these are special points. These points are where the original function and the reciprocal function have stayed the same, and these are called invariant points. So I'd introduced that on the last page, but an invariant point is where the points from the original function and the reciprocal function stay the same. All right, so let's take a little bit more of a look at these invariant points. So invariant points are points on a graph that do not change after the graph's been transformed. So we're calling these reciprocal functions, but we could also call them reciprocal transformations. If you think we've looked at other graphs when we were in the quadratics unit where we were shifting the graph left or right or up or down, or we were stretching the graph, when we take the reciprocal of a function, essentially we're transforming the graph. So these are called reciprocal functions, but we could also think about them as transformations. And so when we transform the graph, if there's points that stay the same, those are called invariant points. And so the invariant points for this reciprocal function would be -1, -1, and 1, +1. But we're going to take a look at how we can get those. So when we're looking at our invariant points, we know that those always happen at y equals 1 and y equals -1. So what we're going to do is start with the original function because it's the easier one to work with, and we're going to substitute in y equals 1 to find out what the x value is. So when y equals 1, we have the function y equals x plus 5. We're going to sub in 1 for y, and we're going to solve for x. So 1 minus 5 would be -4, and this would be -4 equals to x. And then we have y equals -1. So we'd sub in y equals -1, so y equals x plus 5. We'd sub in -1 equals x plus 5. -1 minus 5 would be -6. And so that invariant point, or these invariant points for the function y equals x plus 5 is -4 and 1. and -6 and -1. So notice off to the side here, this is a graph of y equals x and its reciprocal function. We were looking for the invariant points for y equals x plus 5. And so if we want to check to see that that works for the reciprocal function, we can also substitute in y equals 1. So that would be 1 equals 1 over x plus 5. And that gives us x plus 5 equals 1. 1 minus 5 is -4. So again, we have that point -4 comma 1. So that one stayed the same. And we can double check with y equals -1. So we have -1 equals 1 over x plus 5. When we multiply that, or cross multiply, we have -1 times x plus 5 equals 1. So -x minus 5 equals 1. We add 1 to both sides, we have -x equals 6. So then x equals -6. So again, our point stays the same. And because it stays the same for both the original function and the reciprocal function, those are called invariant points. So when we're determining our invariant points, always start with the linear graph. This is the significantly easier function to work with than any fractions. We know that fractions always seem to make things a little trickier. All right, so how does this work if we actually are given an original function and we want to plot new points? Well, if we're given the coordinates of a function and we want to plot the new graph, we literally just take the reciprocal of the function, which would be our y values. So if we're given the function 2 comma 8, the reciprocal function would have coordinates at 2 comma 1 over 8. 4 comma 1 would become 4 comma 1 over 1, which is just 1. We would have -7 and +3 over 1. We'd have -2 and 1 over 0. And we'd have 4 and 2 over 1, which becomes 4 and 2. We have -2 and 5 over 8, so would become -2 and 8 over 5. Now, if we take a look back at this graph, there are some significant points here. So we have 4 comma 1 and 4 comma 1. These stayed the same, so this would be called an invariant point. And notice again, our y value is 1. So anytime that our y value is 1 or -1, we're going to have an invariant point. And if you want to just label that as IP, that's fine, or you could just write IP for invariant point. Now we have another significant point here, and that's when we have -2 comma 0 and -2 and 1 over 0. This is now undefined, and if it's undefined, that means that we're going to have an asymptote. So we're going to have an asymptote at x equals -2. All right, so continuing on here, we're going to take a look at the next example. I'm just going to erase some of what I have here, just to give me a little bit of room. And we're going to take a look at vertical asymptotes. So for a reciprocal function, the vertical asymptote is always located at the x-intercept of the original function. So if we know the x-intercepts of our original function, we then know the asymptotes for the reciprocal function. And so we're going to start off with the graph y equals f of x, and then I'll give you a specific example that we can work with, might be y equals 5x minus 15. So if our original function is y equals f of x, the reciprocal would be 1 over f of x. If the example is y equals 5x minus 15, the reciprocal would be 1 over 5x minus 15. So we're going to try to find what our vertical asymptotes are. We're going to do that by finding our x-intercepts of the original function. Now, if you remember from earlier in this unit, as well as grade 10, when we have an x-intercept, y equals 0. So what we're going to do is we're going to sub in 0 for the function. 0 equals 5x minus 15. And then we're going to rearrange to get x by itself. So we're going to add 15 to both sides. So I have 15 equals 5x. We're going to divide by 5. And we have 3 equals x. And setting that up as a coordinate, we would have 3 comma 0. So that means we have a vertical asymptote at x equals 3. Now we can double check that. For our reciprocal function, we have y equals 1 over 5x minus 15. if we were to think about our NPVs from our previous unit, we know that 5x minus 15 cannot equal 0. And so if we rearrange, that means 5x cannot equal 15, x cannot equal 3. So our NPVs also correspond to our asymptotes. So if I wanted to draw that graph, I would have my original function crossing at x equals 3. Now I'm going to have a vertical line, and then my graph would be approaching, would look something like this. And again, we haven't got into the specific details of drawing that, but we would have a vertical asymptote at x equals 3. And in this case, we would also have a horizontal asymptote at y equals 0. Now, another way to find your vertical asymptote is to find the restrictions on the reciprocal, which is what I just did there. So finding your NPVs also works to finding your vertical asymptote. All right, so continuing on, we're going to start looking a little bit more deeply at how we graph these reciprocal functions if we're given an original equation. So if we're given the equation y equals x plus 2, and we're asked to graph the reciprocal, the first thing we always do is start by plotting our original function. So if you forgot how to graph those, you can always use your table of values on your calculator. But if you remember from graphing linear functions, we just have y equals mx plus b. We start by plotting our y-intercept, which is the b value, and then we count our slope. So plotting that point, we have y equals x plus 2. I'd start by plotting my y-intercept of 2, and my slope is 1. So I'm going to be counting up 1, right 1, up 1, right 1, and so on. And so I would get out my ruler or my straight edge, and I would draw that line. It's really important that you're accurate when you're drawing, so use a straight edge. Your calculator makes a really good straight edge. So we draw all the way through the grid, and then we can put our arrows at the end. So we have that graph y equals x plus 2. So that's our first job, our first step. Now, if you didn't know how to draw that using your y equals mx plus b, you could also find your x-intercept and your y-intercept. And all you need is 2 points to graph a function. So my x-intercept happens at y equals 0. So I could plug in 0 equals x plus 2 and x equals negative 2. So we know that we have an x-intercept at y equals negative 2, or sorry, an x-intercept here at negative 2, and then our y-intercept happens at x equals 0. So we can plug in y equals 0 plus 2 and y equals 2. So if we have our x-intercepts and our y-intercepts, then we can plot that graph. Okay, and sometimes that's a better way to do it if you have bigger numbers, because then, or depending on the scale of your grid, you might not be able just to count your rise and your run. So there's 2 different ways there to graph our original function. Now, the next step is to find our vertical asymptote. Well, we know our vertical asymptote always happens at the x-intercept of the original function. So again, going back to what we just did, our x-intercept happens at y equals 0. So we could plug in 0 equals x plus 2 and x equals negative 2. So that means we have a vertical asymptote at x equals negative 2. So what I would do is I would take my ruler, and I would draw a vertical asymptote at x equals negative 2. And I would draw this as a dotted line. And I would label that VA at x equals negative 2. So the first step is to graph our original function. Then we locate our vertical asymptote. Now we also have a horizontal asymptote, and that's happening at x or y equals 0. So we're going to take and rotate that graph, or rotate my equation here, and I will draw my horizontal asymptote. And I would label that as happening at HA, so horizontal asymptote at y equals 0. All right, now once we have our horizontal asymptote, then we're looking for our invariant point. And so HA at y equals 0. And so our invariant points always happen at y equals 1 and y equals -1. So when y equals 1, that's happening right here. Okay, so -1 comma 1. And our other invariant pointing is happening at -3 comma -1. Now we want to be able to check those or verify those algebraically because we don't want to just trust that our graph is accurate. So we always start with the original function. So we would have 1 equals x plus 2, and 1 minus 2 is -1, so -1 comma x. So our first invariant point happens at -1 comma 1, and our other invariant point happens when y is -1. So -1 equals x plus 2, so -3 equals x. So our second invariant point is happening at -3 comma -1. Now, at this point, we're plotting our reciprocal function. Now, remember from before, as the values of the original function are getting smaller and smaller and smaller, so we're looking in this section right here, so these are small positive y values. Small positive y values, our graph is also, or our function is getting smaller and smaller and smaller and smaller and smaller. All right, and as our graph values or our y values are getting bigger and bigger and bigger and bigger and bigger, our y values are approaching infinity. So they're approaching that graph, going on and on forever. So it should be a nice smooth curve when we're drawing these. So the graph is kind of approaching both asymptotes. And then here, as our y values are getting smaller and smaller and smaller, our y values here are getting bigger and bigger negatives. So it's going to come down like this. I'm just going to undo that one because that one got touched the line. We don't actually want to touch the line. So we're approaching the line but never crossing. And I know it's kind of difficult to kind of envision a graph approaching but never crossing, but that's exactly what's happening here. That graph is approaching 0, but it's never actually going to cross. So taking a look at our domains and ranges, the domain for the reciprocal function, we have a restriction because of our asymptotes. So our domain is x cannot be 0, or sorry, x cannot be -2, and x is the element of reals. And then we have a restriction for our range. Y cannot be 0, and y is the element of reals. And our vertical asymptote happens at x equals -2, and our horizontal asymptote happens at y equals 0. Now notice that our domain and our asymptotes are very much related. And so here we're writing it as a restriction. X cannot equal -2, but the asymptote is actually the equation of a line. So it says x equals -2. All right, let's take a look at another example here. So we're asked to graph the reciprocal of y equals 2x minus 6. So the first thing we want to do is graph our original function, and we're going to do that by finding our x and y intercepts. Again, you could plot your y-intercept and then use your slope of 2 over 1. But I'm just going to start by finding my x and y intercepts. So our x-intercept happens at y equals 0. So 0 equals 2x minus 6. We add 6 and divide by 2, so x would equal 3. And my y-intercept happens when x equals 0. So I would have y equals 2 times 0 minus 6. And so that would happen at y equals -6. And so my coordinates are 0, 3, 3, 0, and 0, -6. So I could plot those 2 points on my grid. So I have 3, 0 is right here, and 0, -6 is down here. And then I would take my ruler and plot those 2 points. All right, so once I have my original graph drawn, then the next step is to look at my vertical asymptotes. Well, we know we have a vertical asymptote at our x-intercept, which we know happens at x equals 3. So we would draw that vertical asymptote at x equals 3. And again, I typically use a dotted line just so we can kind of decipher between asymptotes and the function. And so we're going to have a vertical asymptote at x equals 3. And then we're going to draw our horizontal asymptote as well. And that gives us a horizontal asymptote at y equals 0. All right. Now, and the reason we have that is because of what we've looked at before with regards to the function. As the function is getting smaller and positive, the graph is approaching 0 but not crossing. As those y values are getting bigger, the graph is getting bigger here. So pretty much in all cases with our reciprocal functions, we're going to have a horizontal asymptote at y equals 0. Now, we've graphed our original function, we found our asymptotes. The last step is then to look at the next step is to look at our invariant points. And the invariant points always happen at y equals 1 and y equals -1. So again, don't just rely on the graph, because if you were off by a little bit, your graph might not be accurate. If you're using a straight edge, it should be pretty close, but it's always important that you check algebraically. So when y equals 1, that means we would have 1 equals 2x minus 6. We would add 6 to both sides, so we have 7 equals 2x, and x would be 7 over 2, which is 3.5. So we're going to have an invariant point at 3.5 comma 1. And then at -1, y equals -1, that's -1 equals 2x minus 6. Add 6 to both sides, and we have positive 5. 5 equals 2x, divide by 2, and we have x equals 5 over 2, or 2.5. And so our other invariant point is happening at 2.5 comma -1. So on the grid, we would plot those invariant points. So we'd have an invariant point right here at 1. So that's happening at 3.5. And we would have one here that's happening at 2.5. And so 2.5 would be right here. So again, if you notice, our graph is pretty close, but mine's slightly off. So we can't just rely on our graph. And so from there, we would sketch our graph. So we know as the values are getting small and positive, our reciprocal graph is gonna go this way, and then it's gonna flip up here. If you didn't know this, you could also graph this on your calculator and use your table of values to help give you a guide. So if you forgot this, you do have a way to check it. And then the graph is approaching here. And again, my lines, it's tough with the smartboard here, trying to get it totally smooth, but ultimately you should have sort of that smooth transition with your graphs. All right, so taking a look at our domain and range and our asymptotes, we have our domain for the reciprocal function as being x cannot be 3, and x is the element of reals, and our range y cannot be 0, and y is the element of reals. And then for our vertical asymptotes, we have x equals 3 and y equals 0. All right, so we're going to take a look at our next example here. So in this case, we're given a function. It's already been graphed. We don't know the equation of that function, but we can still find the reciprocal of the function. So normally when we've been doing these questions, we were told to graph the original. In this case, the function's already given to us, so we don't have to worry about that step. The next step would be to determine our vertical and our horizontal asymptotes. Remember that our vertical asymptote happens when we have an x-intercept for our original function. Our next step would be to find our invariant points, or our IPs, and these happen when y equals plus or minus 1 for the original function. And then we're just looking at how the graph is increasing or decreasing. So let's take a look at that. So first of all, we have our original function graphed. We want to figure out where our vertical asymptotes and our horizontal asymptotes happen. Well, if we look at the original function, we have an x-intercept at x equals 2. So we're going to draw or take out our ruler, and we're going to draw our vertical asymptote. And so we'll sketch that in there. And we have our horizontal asymptote happening at y equals 0. And we would label those. So we have our vertical asymptote at x equals 2, and our horizontal asymptote at y equals 0. Now from there, we're going to find our invariant points. And if you notice I'm color coding a lot of this, you might find that helpful when you're doing your work to color code your asymptotes and your invariant points and so on. So when we're looking at our invariant points, we're looking when y is +1 and y is -1. So at +1, we would have an invariant point right here. Change colors there. So we have an invariant point right here. And at y equals -1, we have an invariant point right here. And then we look at what's happening to the graph. Well, as the graph is getting smaller and smaller in the negatives, our graph is approaching that y-axis. And in the other direction, it's approaching the other asymptote. And so for this part of the graph here, as my values are getting smaller and smaller and smaller in the positives, my graph is getting smaller and smaller in the positives, so it's approaching that horizontal axis, and then the graph is approaching this way. And again, you can always double check with your calculator if you weren't sure what these should look like, but that's where your graph should be. And again, I'm not sketching it as nicely as I'd like to. That should be a nice smooth line that's approaching that asymptote. So do be as accurate as you possibly can be when you're doing these graphs. It's probably a little bit easier to draw it on paper. So taking a look at everything that we've talked about, if I have my two functions, y equals x and the reciprocal y equals 1 over x, the domain of the original is element of reals, and the domain of the reciprocal would be element of reals, except that x cannot equal 0, and that's because of our non-permissible value, or our non-permissible value also relates to our x-intercept on the original graph. The range y is the element of reals. The range for the reciprocal would have a restriction y cannot equal 0. Our x-intercept for the original function is 0, 0. There are no x-intercepts when we're looking at reciprocal functions for this reciprocal function. Our end behaviors, if x is positive and the value of x is really, really big, then the value of y is also very large. However, on the flip side, if x is greater than 0 and the value of x is very large, then as y is getting bigger, the graph is approaching 0. For x being less than 0 and the value of x being very large, the value of y, as the value of y gets smaller and smaller, the graph is getting large. The reciprocal function, as x is getting smaller and that x value is large, then as y gets smaller, x is getting closer and closer to 0. All right, so our behaviors here at x equals 0, when x equals 0, y equals 0, but for our reciprocal function, that's where we have a vertical asymptote at x equals 0. So notice we always have that horizontal asymptote at y equals 0, and our vertical asymptote will be determined by either our NPVs or the x-intercept of the original function. And then our invariant points always happen at y equals -1 and y equals +1. All right, so this is a good time to maybe pause the video and try doing this question on your own, and then come back and check to see how you did. All right, so with the magic of video, you can take a look at the example here. So when we're graphing the reciprocal function of y equals 2x plus 5, we first find our x and y intercepts so that we can graph the function. And so the blue line there is our original function, y equals f of x. We can always label that y equals 2x plus 5. And then to find the reciprocal function, we are going to first plot our horizontal and vertical asymptotes. And so we have a horizontal asymptote at y equals 0 and a vertical asymptote at our x-intercept, which is happening at negative 2.5. We find our invariant points. Our invariant points happen at y equals 1 and y equals negative 1, and then we sketch our graph. All right, and if you want, you can also label that as y equals 1 over 2x plus 5. And so it's always important to label our functions so that we know what graph is represented by what function. If you notice in your graphing calculator, whenever you're on a function, up in the top left corner, it will always show you what the equation of that line is. Once we have our graph drawn, then our domain, x can't be negative 5 over 2, so that's our restriction, and y cannot be 0. For our vertical asymptotes, x is equal to negative 5 over 2 and y equals 0. For our invariant points, remember that those happen at 1 and negative 1, so we just substitute those values into the original equation to find our invariant points, and then we can use the graph as well. All right, guys, so that is quite a bit of information there. A lot of it's just introduction to reciprocal functions. In part B, in video part B, for our second day lesson, we're going to be looking at the reciprocals of quadratic functions, but a lot of the concepts are the same, so we won't have to do as much background. We're just going to jump right into those examples. All right, guys, that's all I've got for you today. Have a great day, and we'll see you soon.